Okay, well, I'm happy to be here. I was asked to give a brief review of the state of play before I talk about the new work I'm going to describe. The new work I'm going to describe as work in progress in a collaboration with Phil Sod, who's a student at Stanford, and Douglas Stanford, who was a student at Stanford, whom you all know. And again, let me underline that this work is still in progress, so things might morph a little bit before it gets settled. The motivating question that underlies this work is the question about what are the microstates in quantum gravity from a bulk point of view in gauge gravity duality. Let's immediately back away from that question. Let's forget about the kinds of things that Daniel Jaffers was talking about smearing boundary observables to get into the bulk. Let's go back to the boundary. But let's say we restrict ourselves to talking about, in super Yang-Mills theory, gauge singlet quantities, Wilson loops of various kinds. And let's imagine we reformulate the theory as some functional integral over Wilson loop quantities, e to the minus n squared times some action of Wilson loops. People in the old days thought about this. It's a god-awful mess, okay? But the advantage is if you have these quantities, you can then imagine smearing them and getting into the bulk. The question is, if you have a description just like this, how do you figure out what the gluons are? N essentially just appears as a parameter. It doesn't label an index of degrees of freedom. How do you discover those constituents? So that's the kind of question we're after. It underlies the question of how you find, for instance, the microstates on the black hole horizon and so on. Well, the SYK model is a good place to look at this for a number of reasons. First of all, the basic things that don't have indices on them are things like these bilinears and fermions at different time points, and then you have a Lagrange multiplier enforcing this identification. And one great advantage is you just have two times. This is just bilocal. You don't have every loop. You go from loop space to a space of two times. This, at least when I started thinking about this, seemed like a great advantage, okay? Furthermore, in SYK, you have an exact non-perturbative description of the theory. You know this action in terms of G and sigma precisely. And so you have a complete non-perturbative rewrite of the original fermion problem in terms of these bilocal fields. I should emphasize that you only have this nice description after you average over randomness, as you all know. Here, there's no randomness average, and we're going to have to think, I'm not sure we'll talk about it today, about how much of a price you pay for doing this averaging. It can be a good thing and a bad thing. I think at the very least, descriptions like this that are under control at all are very rare. I'm not sure I know another one. So I think it behooves us to try to understand this question about where in the G and sigma do we find the elementary states of the theory. That's the question we're going to talk about. In addition to being precisely reformulatable that way, also please let me know if I'm starting to write too small. I'm not quite used to the perspective in the room. You can do numerics on this model, and so you can actually figure out a precise signature of these microstates that would be a target for whatever calculation you're able to do. A large group of us, I think 9 of us, whose initials are worked on this problem some time ago. Some of them are in the room. I don't even know if I could recite this. I think Jordan is here. Guy Garari is here. Douglas Stanford is here. I think that's that one. This is Phil, and I think this is me. This is Alex Stryker. Okay, so I think, and the quantity we chose to use as a diagnostic, building off ideas of Juan Maldacena, is to study a relative of what's called a spectral form factor. I think every time today I'm going to work at beta equals 0, infinite temperature. This is a system of a finite number of degrees of freedom. Let's make our life simple. So we want to talk about averaged over randomness. This is just the average of trace e to the I ht, trace e to the minus I ht, averaged over randomness. And written out, it's just the sum over energy eigenstates e to the I em minus en t, averaged over random realizations. And this has been studied for many years in the world of quantum chaos. It's called the spectral form factor. It's essentially the Fourier transform of the energy pair distribution function. We're going to be talking a lot about dimensions of spaces, so let me give a name, L, to the dimension of the Hilbert space of this model, which is 2 to the n, the number of fermions over 2. The 1/2 is because they're Majorana fermions. And one thing we did to get oriented is we actually just computed this numerically to see what there was to see. And so let me put this over here. Here's a graph of that quantity, the spectral form factor, versus time. At time 0, you have a sum over 2 sets of 1. That's L squared entries. So this thing starts at L squared. At late time, you're jiggling around by J averaging, so the only terms that survive if T is enormously large is the M equals N term. You just have L of those. So at long time, this comes back down to L. This probably shows a log-log plot, okay? This we call the plateau. At early time, perturbative gravity, a saddle point in G and sigma, tells you that things decrease. At 0 beta, it wiggles a little bit, but I'll ignore that. So it starts coming down. Make it come down a little more gracefully than that. And then in between, there is an essentially linear behavior that goes very close to 0. I should have pre-drawn this curve. This time at which the thing starts being flat is a time of order L, because that's the finest spacing, inverse of the finest spacing in the spectrum. This ramp, as we called it, is essentially linear. It varies like t. It runs essentially from time 0 up to time L at a linear slope. It's become clear more recently, due to work of Hrant Garibian, a student at Stanford, Masaki Tezuka, Masanori Hanada, and myself, that you really can follow this ramp underneath this slope. It really continues, and in fact, it continues to a very early time. It's called the Fowlis time. That's a time like log n. Very short compared to these exponentially long times. And the height of this early time is order 1 up to logarithms. So you have this very long ramp that goes from 1 up to L over this very long time interval. These are the things we'd like to explain. We understand the origin of this. The origin of this ramp plateau structure is the random matrix dynamics of the energy eigenvalues, which is characteristic of quantum chaotic systems. As I said, this quantity is essentially the Fourier transform of the pair distribution function, which in random matrix theory is given by the famous sign kernel expression that looks like this. This is going to be hard to see. Is that, well, at early times, large energy differences are important. You can avoid this rapidly oscillating sign. You have the Fourier transform of this, which gives a linear ramp. The magnitude of the ramp is order 1 over L squared. That's perturbative in random matrix theory, but it's of order e to the minus n in SYK. It's a non-perturbative effect in SYK of the strength of a saddle point. It's a good target for a saddle point. At times of order L, this oscillation starts being important because the energy differences are very small. Sine squared of L is something like e to the I, e to the n, some extremely peculiar non-perturbative effect that must be involved in understanding these microstates. And in fact, a very distinctive signature of these microstates is this ramp ending in the plateau at this very late time that corresponds to the finest energy difference. So these are the things that we'd like to be able to explain. In particular, we'd like to be able to understand them from this G sigma description. Now, when this stuff started becoming clear, I guess almost a year and a half ago, I was very optimistic. I said, look, we have this complete non-perturbative description. These bilocal things are far better than loop space. That's where those of us that grew up on gauge theory started. We got, well, it was a very dispiriting experience to try to understand things in loop space. Bilocal things, to my way of thinking, a function of 2 variables is almost as good as a function of 1 variable. So this is going to be easy, all right? So a number of us tried to understand how we could understand in terms of these bilocal variables phenomena like that. Well, it's a year and a half later, and I have to tell you that I think I was over-optimistic. So a lot of what we've been doing during most of that period is to realize and then try to even further simplify the problem so we can make some progress. All right, so we've gone from gravity in the world to the world of anti-de Sitter space to the world of SYK. I have to take you one further step away from where we live. Okay. So the direction I'm going to describe that the 3 of us are working on over the last couple of months seems to have some promise, and that's what I want to tell you about. Well, in order to understand how to tame these 2 times, I have to remind you where those 2 times come from. I've already said a little bit about it. Let's start here. In a Lagrangian for SYK, we have an interaction term that looks something like the integral dt prime from 0 to t, some randomness variable. I'll imagine that we have, in the jargon, Q equals 4 for this talk. 4 fermions coupled together. This is some random coupling, psi A of t prime, psi B of t prime, psi C of t prime, psi D. This subject is not an optimal subject for a blackboard talk because there are these long equations you have to write out. So we'll make do. And then the randomness is given by a Gaussian weight. And then we imagine integrating out this Gaussian weight. The crucial thing is that this Gaussian weight is independent of time. And so if you imagine this is a line, a timeline from 0 to t, you have these groups of 4 fermions, and integrating out J couples groups of fermions at all different times, t prime, t double prime. And so you end up with an integral dt prime, dt double prime of psi at t prime, psi at t double prime. So you have pairs of fermions at all different times talking to each other. And if this had an index A at t prime, and this had an index t double prime at A, you would end up grouping these things together and calling, after rearrangement, and calling this G of t. So the non-locality comes from the time independence of the randomness. Now, the time independence is a good thing. It lets you have, for each realization, a genuine Hamiltonian system. But it's making a big headache for us here. So one of the things we said is, look, we're desperate. Why don't we let these couplings not be independent of time? Let's let them depend dramatically on time. In fact, let's let them fluctuate randomly at every successive time. So let's make the replacement that the covariance J, or the variance J is independent of time, goes to J of t, J of t prime, equals some size, delta function of t minus t prime. So these are Gaussian distributed random variables that are uncorrelated except at the same time.
Does that mean you're effectively working at infinite temperature?
Yes, yeah. Lenny's comment is that whenever you start jittering a Hamiltonian like this, you tend to pump energy into the system. So it's hard not to go up to infinite temperature. This is a finite Hilbert space, so it's okay, who cares? Okay. Not if you have 2 to the 34th fermions. They just,
That's finite, whereas time is continuous.
oh, yes, well, yes, we're going to have to do some regulation here. Okay, but this is one dimension. There's no big ultraviolet divergences. It's not too hard. Okay, so then if you do the same kind of calculation you did here, you would find that the fermions in this lump would only interact with the fermions at the same time. And instead of getting G of t prime, t double prime, you would just get G of t prime and a Lagrange multiplier at one time. You would go from bilocal things to functions of one variable. This is a big improvement. Okay. And so this is what our proposal is. Now the question is, when we make this rather drastic change, have we thrown out all this interesting structure? All the structure that is diagnostic of the discrete states? And the answer is no, not quite. There still is a little bit left, and that stuff is interesting. So let's ask, what do we expect a system like this to behave like? So let's just think about the operator. In ordinary SYK, we would have some Hamiltonian, and this would evolve it in time. In this situation, at every time step, we have a slightly different Hamiltonian with a different set of J's. So we have e to the IH1 delta t, that's a small time interval, e to the IH2 delta t, e to the IH3 delta t. I think you get the idea. Okay. And let's call this product some unitary operator. It's unitary. We're in the realm of operators on Hilbert space. Each one of these is unitary. You get a big unitary after this. Just like this is unitary. But the Hamiltonian changes step by step. Okay. This idea of having Hamiltonians that change, this thing is called a Brownian circuit. And if you have a finite time spacing, this will be what's called a random quantum circuit. You'd apply random gates. These kinds of things actually have a long history in physics of lots of kinds. I think Lenny, you and Michael Peskin and Tom Banks wrote a paper using this. I can't even remember when, a long time ago. People have studied this for a long time. In quantum information, Brownian circuits and random quantum circuits are heavily used, for instance, to try to produce good approximations to random unitary operators. Okay? So I actually had produced a list of references, but another disadvantage of giving a chalk talk is the list of references was almost a page, and it would use up half my time to read it to you. So those of you that have worked on the subject, you know who you are, okay? And probably I know who you are. Yes. Yes. Yeah, that's an infinite. I mean, the only thing that happens at infinite temperature, and I elided it, is this thing wiggles a little bit. But yes, yeah, it's a random matrix, so yeah. So here, how do we think about this chain of little changing Hamiltonians? Well, one way of thinking about it is to think about the space of the unitary group on the Hilbert space. Here's the identity. You act with one of these things, you move off this way, you do a random walk on the unitary group. If the Hamiltonian is chaotic, and we know SYK, if Q is not equal to 2, is a very chaotic system, we expect this random walk to eventually cover the entire unitary group. Okay?
So it's still random, even though the H's are have a very particular point?
Yes. Because, I mean,
Each e to the IH delta t is not a random
that's right.
unitary, right?
That's right. But you're taking a product of different Hamiltonians. If it was just one Hamiltonian, you would, for instance, conserve energy. And you wouldn't cover all unitaries. But the fact that you're changing is enough. Okay? And this gets into the theory of K designs and stuff. So this is the way what happens. So our expectation, and it is true, is that this happens. What is the analog of computing ZZ star, which for a Hamiltonian system was trace e to the IHT, trace e to the minus IHT? Well, the natural thing is to take trace u of t, that string of little Hamiltonians, u star of t. I take the star instead of the dagger so I don't have to reverse the order of that product. Okay? And then I would, sorry?
2 traces.
Thank you. And then I would imagine averaging it over randomness. Here I would average over one realization of J's for all time. Here I average over a whole trajectory, J of t, the whole sets of these Brownian motions. Okay? And the question is, how does this behave? Does it tell us anything, for instance, about the finite dimensionality of the Hilbert space? Well, here's a graph of what you'd expect. T here is the amount of Monte Carlo time that you evolve this Brownian process. When did I start? 2:30? So I'm going pretty slow. All right. I may need to indulge myself a little bit. I'm just warning you, kitten. At time 0, u is just the identity, so the trace is just L. You have L times L. You get L squared. As you evolve in time, this thing becomes less close to the identity, and in fact, you generically expect things to decrease exponentially. At long time, this thing is positive. It can't quite go to 0. What is the result at long time? At long time, you should be able to replace this complicated process by the expectation value of U star in a Haar random ensemble of unitaries. So here you expect the thing to be a constant given by this. This you can evaluate just using random unitary integrals. You get the answer 1. So we expect this thing to go down to not a plateau, but a floor of height 1. Okay. Notice there's not this interesting ramp plateau structure because you're changing the eigenbasis at every step. But still there is this little indication. Notice the fact that this is a finite ratio, a ratio of L squared, is an indication of the finite dimensionality of the Hilbert space. And so now the goal is, can we compute this from these collective variables, G and sigma? We know what the answer is, but can we actually see it from these variables that seem like they might have something to do with bulk descriptions? And the answer is yes, we can do that. Here we go. Smaller than the plateau? It's actually much more related to this, the bottom, the early part of the ramp.
Because you just explore much more of the unitary space?
Well, there's that too. Yes, I think they're both related to that. You'll actually see how they connect in a little while. That's correct. It's because you don't have a fixed set of eigenvalues of which you can diagnose the rigidity between them. All right, at every different Hamiltonian, you change the relative eigenbasis. So you have the eigenbasis shifting around, washing out the delicate correlations. You'll see in a bit how we can reconstruct a ramp out of this, assuming, well, yes, I hope so. Well, so let's set up this problem. We need 2 copies of the SYK model. We have a left copy and a right copy to make the 2 copies of this unitary. The J's are the same on each side, but the J at this time is correlated just with the J at this time. Okay? So when we do the integral, we get products of fermions. Either these fermions have to be on top of each other on the left side, or they have to be at the same time on the right side. Okay. Well, so here you'd have a collection psi, 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 right on top of each other. Now, there's a funny thing about Grassmann's, that psi times psi is 0. Okay? But on the other hand, the delta function correlation of the noise, Jj is correlated with a delta function, so the variance becomes infinite at equal time. By carefully smearing, you realize that the right rule is that when psi of t plus epsilon goes to 1/2 as epsilon goes to 0. So you can just replace these on-site terms by a pure number. So nothing happens if you just had one theory. In fact, there'd be no dynamics left. You would just get a pure number. And in fact, that pure number would give you this exponential decay. In this 2-copy system, this 2-replica system, there is another part where you have this 4-fermion thing on the left coupled to the 4-fermion thing on the right, both at the same time. So you have the interaction that can still be present is a 4 fermion thing on the left coupled to a 4 fermion thing on the right at the same time. That's because I'm short of time. I think I'm going to just write down the answer for what you get and motivate the terms. So you find on doing this average that you end up with an integral over g left right at time t prime d sigma left right at time t prime. These are just time. These function, an integral over two sets of functions, the exponential of minus n over 2, the integral from 0 to t dt prime, a pure number over this colliding piece. You have 4 fermions colliding, a half times a half times a half times a half gives 1 over 2 to the 4th. So you have a 2 to the 4th here. This is some constant I won't write. The 2 to the 4th tells you it comes from the colliding term. Minus g left right of t prime to the 4th. That's this 4 Fermi interaction here and here. 8 fermions, 4 g's, plus sigma left right of t prime, g left right of t prime, enforcing a Lagrange multiplier minus psi left of t prime, psi right of t prime, sigma left right. So sigma, when you integrate it out, is a Lagrange multiplier that says g is equal to this bilinear of fermions. And then you also have kinetic terms for the fermions. And you're doing a functional integral over fermions as well. This part just gives you some kind of determinant involving sigma. And so you see you have a determinant raised to the nth power, since you have n of these, involving sigma, and then you have this functional of a function of one variable. This should give the answer. So if you then actually make the ansatz that sigma and g are constants, try sigma t, GOT constants, this determinant is easy to evaluate. Left and right combine together to make a Dirac fermion. This is just the determinant of n Dirac fermions, which is 2 cosine t sigma over 4 raised to the nth. And so let me just call these constants sigma and g. Then you end up, at the end of the day, if sigma is imaginary, the cosine turns into a cosh. If time is long, it goes like e to the t sigma over 4. with an n. So you have an action that looks like n log 2 plus n times time, because you're integrating constants over time, some number times sigma minus j over 2 to the 4th plus jg to the 4th minus sigma g. And there are all kinds of constants in here I'm not keeping track of. And then this is just an integral over these constant values, and all you want to do is find a saddle point. Well, there's an obvious saddle point when g and sigma are both 0. Everything drops except this e to the minus nt over 2 to the 4th. So you have 2 to the n, e to the minus nt with a constant. Well, this is this initial exponential decay starting at L squared. So that saddle is the early time decay. But there's another saddle. You vary this and you get some equations that look like g equals some number from varying sigma, and 4g cubed equals sigma. So these have a non-trivial solution. It turns out g is equal to some number times I. Sigma is equal to some other number times I. And these can be plus or minus pairs. And so you have this other saddle point, and the constants are arranged so that on this other saddle point, the action is 0. So you have a contribution from another saddle point that looks like 2 to the n, that looks like e to the 0 times nt. And e to the 0 is 1. So there's this other saddle point that gives a contribution equal to 1. And so, in fact, you reproduce this expected behavior from simple saddle points. Now, there's a lot of things to be said, and I've just chewed up all my time. Let me just collect a subset of them. I think maybe the most interesting thing to talk about would be, you've now reproduced this picture, but this picture is a lot more boring than this picture. How would you get back and try to incrementally climb back up the ramp? Well, the idea is that you can do something intermediate between this entire Brownian circuit and pure SYK. Here's left and here's right. Rather than just sort of running random j's all the way up, suppose, I don't need both 2 lines. If L is just a pure Brownian circuit and you ran noise like this, how about if you did the following? You ran some noise that looked like this, but then after a certain segment, you just repeated the noise identically. So here you'd have u of t, u of t, u of t. So you repeat the same unitary k times. So this is kind of intermediate. You don't have a complete Brownian circuit, but you don't have SYK where you'd have a fixed thing. Then ZZ star would turn into trace u to the k of t, trace u star of t to the k. Well, suppose you've run t long enough that the thing really looks like a Haar-random unitary. What is this equal to in a Haar-random unitary? This quantity for Haar-random, if this is k, it's exactly equal to k. So at k equals 1, it's equal to 1. At k equals 2, it's equal to 2. At k equals 3, it's equal to 3, and so on. It's an exactly linear ramp until you get to k equals L, at which point it levels off. It's exactly a ramp for much the same reason it's a ramp in random Hermitian matrices, because of level repulsion. Just unitary matrices, things are much cleaner because you don't have edges of the spectrum and crap like that. Okay. So this is something we could try to reproduce from G's and sigmas. The new ingredient is you don't just have one G of T and one sigma of T. If you now have this situation, the fermions here are correlated with the fermions here, but the J here is also the same as the J here and the J here. So you have k different things to include. You don't have to include an infinite amount of bilocality. You just have to include like a 4 bilocality. So the new variables are, for instance, G of T, left, right, say, S prime, where S is a segment index that tells you where you are, which of these 4 segments you're in. So these run from 1 to k. So this is a k by k matrix of functions. You're building up the non-locality of SYK incrementally. This matrix is a non-local object, but it's not one of these horrible bilocal functions. It's just a 4 by 4 matrix. You can then try to look for saddle points in this space. And in fact, we were able to find a natural set of saddle points. Saddle points that actually each have action 0. And so if you add up k saddle points with action 0, you get the number k. So this contribution at k equals 3 came from 3 saddle points, just added up. 3 times 1 equals 3. Okay. So we see the ramp as coming from a very simple set of saddle points. They actually have a rather natural interpretation in terms of SYK, and at least metaphorically, you could think of taking this interval very small and k very large and map onto some solution of the pure SYK equations. We haven't been able to do that yet, but it's suggestive that something like that would work. In pure SYK, we have a ramp that is proportional to t. This saddle point breaks time translation invariance, and so you have a different saddle point at every value of t. It's a simple way to get a ramp that's proportional to t. You have t different saddle points of action 0, and you sum over those t sets. That gives you a linear ramp. That's the idea. But of course, something happens here. This craps out at k equals L. Somehow these different saddle points are not independent when k is as large as the dimension of the Hilbert space. And this is the part we're most confused about. Okay? You would think, if you have 20 functions, we would be able to directly compute this plateau. Here we're not talking about bilocal functions, we're talking about ordinary functions. It's just an integral over 20 functions. We haven't been able to figure out what it does yet, but I still have my hopes up. One hint of what might be happening, and this will be the last thing that I'll say. Is the following. This is an extraordinarily simple thing that's produced by Haar random averages. We could look at something more complicated, like trace u squared, u star squared, a single trace object. This we could write in terms of g's and sigmas, But we can also evaluate it using Haar random averages to get a guess of what it is. Using standard technology for evaluating Haar random averages, so-called Weingarten functions, you find that this thing has the answer this is equal to L plus 2 over L plus 1, which is equal to 1 plus the sum of little l equals 1 to infinity minus 1 to the L, 1 over L to the L. This 1 just comes from a saddle point of the kind I was describing, an action 0 saddle point. But this functional integral seems to contain a lot of other stuff. It's an infinite series in e to the minus n. It's an infinite series of instantons. Okay? Notice there's no t here, so these things cannot be constant on the interval. There's some kind of lump that we don't understand yet. Yet they must be here. Notice this integral is full of magic. These coefficients are pure integers with an interesting oscillating sign. And further notice that this series, it's not like a dilute gas of instantons that has an infinite radius of convergence with a 1 over L factorial. It has a finite radius of convergence at k here is 2, equals L plus 1. That's a fancy way of saying L equals 1. Okay? This is just the place where you expect the plateau to cut in. So there's a speculation, anyway, that this infinite series of instantons will pile up, that this is the thing in terms of g and sigma that will tell you that these saddle points should not be counted independently. And these effects will pile up and tell you that a plateau must start. All right, well, I've gone on too long. So here's the program as we see it now. Finish the analysis of this Brownian circuit. In particular, figure out where this plateau comes from. Translate these saddle points as much as we can into SYK saddle points. Some of this we can see how it works. These instantons are a mystery, but they've got to be there. This is just an integral. This isn't some mythical string field theory. It's just an integral over functions of one variable. Okay? And then we have to decide what, if any, implications there are for quote-unquote real gravity. Let's say ADS CFT with super Yang Mills. Well, we'll keep you posted. Thanks. I'd say that again?
Which part of the story depends on how local is every step in the Brownian circuit?
Yeah, you will only get isomorphic results to the result of Haar integrals if the time is long compared to the time to relax, long compared to the Thouless time, which in this case is log n. In order to make it fit with SYK, you probably have to make the interval short compared to that. So there will be a crossover. And that will be part of the difficulty in making that correspondence. But to make the curve look just like this, you imagine that this time of the Brownian circuit is long compared to the time when the thing hits bottom. Okay, this time is probably log n. It's one of these Thouless time estimates.
So with the usual SYK, there are these tensor versions where you don't have the randomness.
Mm-hmm.
So is there a
Yes, there probably is. It probably will work somewhat similarly. The defect is we don't have a G sigma description of that. And without a G sigma description, we can't answer the question we started with about what it means from the bulk. You can do Brownian circuits on all kinds of stuff, and it will work sort of similarly. The real question is this alternative presentation. That's the power of this SYK with random couplings, because it gives you another language to understand those results.
I see. There's no analog of that for the tensors?
No.
I have a question.
Yes.
Normally, when you find the saddle point, it's actually zero. Wouldn't we worry that the fluctuations are large?
Yeah. It turns out these integrals are miraculous, and I didn't have time to explain this, I should have, that the integral in some sense localizes on the constants. And for reasons I think you taught us, that let's talk about the one segment thing. You have a fermion action that looks like psi d psi integral dt plus sigma of t psi psi. You can reparameterize time. This kinetic thing is independent under time reparameterizations. But sigma goes to something like, sigma of t goes to sigma of t, what, over the reparameterization, f of t, if t goes to f of t. So by choosing a reparameterization, you can kill almost all the time dependence and make sigmas constant. And so, in fact, the integral over g's and sigmas localizes onto constants. If the sigmas are, if this action only depends on constant sigmas, the Lagrange multiplier piece is the only thing that sees non-constant parts of sigma. They set the non-constant parts of g to 0. So the integral reduces to constant sigmas and constant g's. So there's no room for unpleasant fluctuations. This is what almost certainly does not happen in these higher k formulas. It has to have other stuff, for instance, these instantons, which are not constants. And so part of the thing we're trying to understand is exactly, there is a lot of localization going on, but exactly what configurations does the higher k integral localize on? And that's part of the ongoing research. But there's magic in these integrals. There's something we haven't fully understood. The fact that these things localize, the fact that these coefficients are so simple, almost all the guts of this integral has been sucked out because it's just trying to reproduce group theory somehow. And that somehow is a clue to some of the things that happen to gravity at late time.